This is Lecture 3K for Calculus 1 on orthogonal trajectories. We have to start with some vocabulary. You have probably heard the words perpendicular, orthogonal, and normal. They both refer to items, things, crossing at right angles, but it's the things that are crossing that make the difference in where you use the word. If it's two lines that are crossing, two streets that are crossing, you say they are perpendicular. If you're talking about two vectors or two families of curves, not necessarily straight lines, but curves, then you say they are orthogonal. And if you have a plane, consider a plane and a line that is perpendicular to that plane, the line is at right angles to that plane, or you have a vector, you say that vector is the normal to the plane. So then the word normal refers to a vector or line that is at right angles to a plane. This is very useful in describing surfaces, especially curved surfaces. The term trajectory is used here because there's the idea that the curves describe the path of some particle or some moving object. With the words orthogonal and perpendicular, we have the idea of the right angle. We also have another connection. If two lines are perpendicular, their slopes are negative reciprocals. If two families of curves are orthogonal, their derivatives are negative reciprocals. Remember, derivative will pertain to a straight line where, a slope pertains to a straight line, whereas the derivative isn't so limited. So this idea of having negative reciprocals connected to right angles occurs both with the word perpendicular and the word orthogonal. When we're talking about families of curves, we will have some functional expression for them or some equation that describes these curves, and it will include some constant, in this case c. X times y equals c. Oh, by the way, these don't have to be functions. And here's another. X squared minus y squared equals k. Right. To generate the family of curves, you vary c. For example, if I let c be 1, I would get a curve in the plane. I let c be 2, I get another member of the family. I let c be 5, I get yet another member of the family. The same thing with k, and that's how these curves are drawn. Here's an example. I believe these are scaled exponents here. I'm not sure what these curves are. Okay, but it was an example that I stole from the internet showing families of curves that are orthogonal. So I just wanted to give you some pictures of some curves. They're a little bit hard to draw at times. But the idea is that where these curves cross, right here for example, or here for example, or wherever they cross, if you could compute the slopes right at that point, the slope along one curve would be the negative reciprocal of the other. But when you're talking about families of curves, we can't sit and compute every single point in the plane to see if it holds everywhere. Instead, we just look at the derivative. Here's another example. I'm not sure if it's easier or harder to read when it's in color, but you have these circles of different radii in blue, sort of increasing horizontally, and then you have circles of the various radii in red. And they're located vertically, or they're increasing vertically. That makes a family of orthogonal curves. And again, if I could look at every single little spot, like right here, I'd find they were at right angles. Right here, I would find they're at right angles. But instead of trying to go through and pick every little spot, I just get the functional form or the equation for these families, and then compute the derivatives. And here's an example of computing the derivatives for the example that I showed a couple slides ago. In that case, one family was described by x times y equals c, and the other, it was x squared minus y squared equals k. So I'm going to take the derivative of these functions using implicit differentiation. So I apply the derivative operator to both sides of the equation. The derivative of a constant here is 0, so that side's done. Over here, I have two functions multiplied together. So I have to use the product rule. I have to hold x constant and take the derivative of y. Then I hold y constant and take the derivative of x. Well, the derivative with respect to x of x is 1, so the second term is just y. The The first term, though, dy by dx is not specified, so I just have to leave it as such and then solve for it. So the derivative for this family of curves is minus y over x. Note that the c is gone. Right? All these curves have the same derivatives. Okay, now look at family 2. In that case, it was x squared minus y squared equals k. I'm taking implicit differentiation again, so I apply the derivative operator to both sides of the equation. Over here, the derivative of a constant is 0, so I can just write it like that and get it out of the way. Now I have x squared minus y squared. So because of the linearity of the differential operator, I can just apply d by dx to the x squared, and then it's minus d by dx times the y squared. The derivative of x squared is 2x. That's done. Okay. Now I'm left with this term, d by dx of y squared. Here's a case for the chain rule. The y is some unknown function of x raised to a power 2. The outside function is something squared, in this case y squared. The inside function is y. So first I take the derivative of the outside function and get the 2y, just by using the power rule. Then I have to take the derivative of the inside function. That would be dy by dx. I just leave it like that and solve for it. And so here is the derivative for that family number 2. The derivatives are negative reciprocals because minus y over x is a negative reciprocal of x over y. If you drew this family of curves, they were a little hard to draw, so I didn't graph them, but you would see that the lines appear to cross at right angles. In fact, they do cross at right angles, but we can't calculate that, but we do calculate the derivatives. Orthogonal trajectories occur in, well, they occur in particle physics. I hope some of you are going into physics. So you use them a lot in particle physics, this idea. In a rather everyday sense, they have to do with terrain maps. Now, on a terrain map, the curves on the maps are locations of equal elevation. Curves that are orthogonal to the equal elevation marks would be the paths of steepest descent. So if you were on some kind of a mountain and it had a varying elevation, the fastest way down is to go perpendicular to the curves of equal elevation. Now I'm going to work out an example and then give you the graph, show you the graph of the result. I want to determine if the following family of curves are orthogonal to make orthogonal trajectories. Okay. The lines to the origin are going to be one family of curves, and that's y equals mx. So this is a bunch of straight lines all going to the origin, all having different values of slope. So the constant here that gets varied is m, the slope. The other family are concentric circles located at the origin. So they all have the center at the origin, but they have different radii. In this case, the r, the radius of the circle, is the constant that gets varied to generate the members of the family. So what I do is take the derivative for each family. For the lines, I write it like this. I had y equals mx. I'm going to divide by x. So and now take the implicit differentiation, applying the d by dx to both sides. The d by dx of the constant m is 0, so that's done. Okay. Now we go back, and we see here we have y over x. I prefer to write this as y times x to the minus 1 and use the product rule. For the product rule, I have to hold the y constant and take the derivative of x to the minus 1. Then I hold x to the minus 1 constant and take the derivative of y. When I do that, I get this result. All right? And I solve for dy by dx, which equals y over x. Which actually you could have decided just by looking at the equation. However, I wanted to work it out just to show you the steps that you go through. Now let's do the same thing for the circles. So I had x squared plus y squared equals r squared. I'll just take the derivative of the x squared plus the derivative of the y squared. And here on the other side is the derivative of that constant. The value of that is 0, so that's done. the derivative of x squared is 2x. Okay. Now, we're left with this term of taking the derivative of y squared. This is another case for the chain rule. The outside function is something squared, the inside function is y. When I take the derivative of something squared, I get 2y right here. Then I have to take the derivative of the inside function, I get dy by dx. I solve for dy by dx, and the answer is minus x over y. These are negative reciprocals. Y over x is a negative reciprocal of x over y. In both examples, we had very simple results. It might not always be the case. Okay, so here's a graph of the situation. The blue lines are the straight lines to the origin. The red lines are the concentric circles centered at the origin. And every place where these intersect would be a right angle, because their derivatives are negative reciprocals. So in a practical sense, if you are on the top of a completely conical mountain, the fastest way down would be a straight line to the bottom.